In section 1.3, we're going to get some more details about functions and then also talk about graphing. And so these are the 6 objectives that we will cover here today. So first of all, what does it mean for a function to be increasing, decreasing, or constant? Really, it is exactly what you think. If you visualize the graph of a function, as you move from left to right, watching the graph, as you move from left to right, if your pencil or pen would go up as you draw out the graph, that's an increasing part, meaning as x gets bigger, y gets bigger. Decreasing is the opposite. Going down as you move from left to right. So as x gets bigger, y gets smaller. And the mathematical way to say this is exactly what we said here. If you have x1 is less than x2, so smaller x1, bigger x2, you have an increasing if the function values, the y values do the same. Smaller f of x1, larger f of x2. Increasing, smaller x1 with a larger x2, to flip, the function value at the smaller x is larger than the function value at the larger x. So that's where we have decreasing functions. Good morning. Now, where is the function constant? The function is constant where the graph is flat, meaning as x marches along to the right, the function value doesn't change, so it's the same y. And so that's what we always mean by constant in mathematics, is that it's not changing. So we talk about variables, we talk about constants. So variables are things that change, constants do not. And so where the function is constant means that x changes, y does not. That's where the slope would be 0. Because the change in y would be 0. Y is not changing. So just some pictures to help us see these. For the first one, kind of the top left one, looks like this. Let me zoom in and focus. Notice that as I trace the function from left to right, the entire time the pen would be moving upwards. And so oftentimes we talk about increasing or decreasing on an interval, so you would specify, say, the interval from x1 to x2, meaning we're just focusing right in there on that. Notice that the function is moving upwards there. What does decreasing look like? It's moving down. And so if we just were to focus, this entire function is decreasing, but in particular, if we were to focus on the interval from x1 to x2, you can see that the function moves down as you trace it from left to right. And then a constant function, which is what's over here, that's just a horizontally flat piece. And so this function is constant. It's always whatever this value of y is. It does not change. Any questions on the pictures here in this slide? All right. So, some of your homework problems might be something like this. State the intervals on which the given function is increasing, decreasing, or constant. So when we talk about intervals, remember we're saying over which x values is the function increasing, decreasing, or constant. And so for this means to list the x values. So it's about the x values at which the function is increasing, decreasing, or constant. And so maybe on the screen it's a little hard to tell. I'm going to use this high-tech camera and zoom in. And let's see what's going on over here on the far left. So on these problems, just look from the left to the right. And as you start at -4, which is where this function starts, what do you think about this piece of the function from -4 to -2? It's constant. It's just a flat piece. And so from -4 to -2, the function is constant. And so we're going to list intervals where the function is constant. We're going to list intervals where the function is increasing. And we're going to list intervals where the function is decreasing. And so our first interval, the far left interval, is constant from x starting at -4 and going to x ending at -2. For these intervals, we will use the parentheses notation because where it changes, it's technically neither increasing, decreasing, or constant because it's changing from one to another. And so we want to leave these as open and not include the endpoints. Remember, we square off brackets on interval notation when we include the endpoints, and then we use the parentheses where we don't include the endpoints. So up to but not including -2, the function is constant. Once I pass -2, notice what my pen does. It's moving upwards from left to right. So that is increasing. It's increasing from, and remember, we're looking over the x values. So it starts increasing when x is at -2. Here is where it ends decreasing, but that's when x is 0. So from -2 to 0, the function is increasing. Now, starting at 0, x is 0, this piece of the function is decreasing. And don't get tripped up by the x-intercept. We're still decreasing beyond that. It's still moving down. And so from x equals 0 all the way to x is equal to 3, the function is decreasing. So from 0 to 3, the function is moving downward. And then finally, once we hit x is equal to 3, we trace the rest of the curve. It's moving upward, so that's another increasing piece. And so I'll put my union symbol here, meaning or, starting at x is equal to 3 and going to this x value right here, which is 4, the function is increasing. So that's visually what it means for a function to be either constant, increasing, or decreasing. We list the x values over which the function has those characteristics. How'd you do with that? Good. The next slide is about definitions of relative or local maximum and relative or local minimum. And so depending on the textbook that you're looking at, the textbook might just call it a relative maximum and it might call it a local maximum. That means the same thing. Relative max or local max, those mean the same things. I believe our book uses the word relative, but I wanted to make sure that you had heard the word local, because when you move on to pre-cal or Cal 1 and beyond, they might use the vocabulary of local. So that's why I put that in here. A function value, f of a, is called a relative maximum of f if there exists an open interval containing a such that f of a is greater than f of x for all values not equal to a in that open interval. So that's a mathematical speak for saying we are looking for any peaks, any high points, because that's what a maximum is. A maximum is a high point. And so when we're looking for relative maxes, we're looking for peaks in a function. We'll draw a picture. We'll look at some pictures here in just a second. Alternatively, the relative minimum is looking for the valleys. So any valleys that you might see, any low points. And I'll explain what relative means as well. So relative maximums are the highest points relative to points near it. Relative minimums are the low points relative to points near. Peaks for relative maxes, valleys for relative mins. So here's what a relative max might look like. As you look at, say, this window from here to here, notice that you hit a peak at the value x equals c. That means close to points near c, f of c is the highest value. So that's what we mean by relative, close to. If you hit a valley like this, it's the same thing, but it's the relative minimum. I'm going to draw one more picture just to give you a bit more detail. Let's say I had a picture that looked like this. Any peak is a relative max, and any valley is a relative min. So So what you're thinking about is a moving window. This is the relative or the local part. Local meaning close to. So if you think about what's local to us in this community, we're saying what's close to us. So close to points, and so you start to move this window and notice that there aren't any peaks in here until I get to this moving window right here. This peak right here is a relative or local max. And then we move the window that we're observing until we find a valley. And so we find a valley right here. This is a relative min. But you can have more than one. And so by the awkward way I sort of drew this curve, we do have another peak here. This is another relative max. And as you move along, you see another valley right in there, and that is another relative min. Okay. Notice that we describe where the relative maxes and mins are by their x values. And so you tell where it occurs by the x value, and then the actual max or min value of the function is the y value. Any questions on this slide? We're just looking for peaks and valleys. Yes, ma'am. No, you say where the maxes or mins are, so where they occur is the x's, and then the actual maximum or minimum value of the function is the y. We'll do some that I'll show that a little bit better here in just a second. Okay, so right here, it says use the graph to identify the relative maxima or minima. So maximum is singular, so it's just a little grammar here. Maxima, ending like this, means it could be plural. And so maxima and minima, those are plural. Collectively, we call the maxes and the mins the extreme values of the function. So you can also see the vocabulary that we're looking for, the extrema of the function, the extreme values, which are your maxes and mins. And so mathematically, extrema collectively means maxima and minima. Okay, so this particular graph, it already highlights where they are with a red dot and a blue dot, but you see as you trace the curve along, you've got a little peak there. Thank you. So that occurs at x equals -1. So we have a relative max at x equals -1. Now for this one, the y-axis isn't scaled super well, and so telling what the value is would be just whatever this y value is that associates with that red dot. But since it's really just saying basically where they occur, that's not really a great possibility for this particular example. And then we keep tracing the curve along until we get to the blue dot. That's our low spot. So that's going to tell us our relative min. And the relative min occurs at the x value of this blue dot, which happens to be 1. Now you may be sitting there and thinking, Krista, the highest value of this function is not at -1. And you're right. Because what happens as you trace the curve further to the right, the function zooms up to positive infinity. And so the global maximum is positive infinity. If we were to look at this function globally, the whole function, there would actually be no max because it continues to get bigger in the positive direction, going to infinity. But locally, so that's the difference. Locally means we're just kind of looking at a little window, and notice that as I look at a little window, I get a peak there. So any peaks or valleys are your relative or local maxes. Same thing with the min. The function does go on down to negative infinity on this side. So the global minimum doesn't exist because it goes down to negative infinity. But the local or relative min exists anywhere you have a dip, a valley. Okay? Those are important characteristics of a graph because look what happens at a minimum. A minimum is where the function changes from decrease to increase. And so think about this. If you were owning a business and you were looking at your profits, right? And so if you're not selling very many, your profits are probably going down because you've got a lot of costs that go into making those. But once you hit a certain number of sales, your profits are probably going to start going up. And so knowing where that point of change from decrease to increase is, that's important, okay? On the other hand, look what a max does. A relative max is where the function changes from increase to decrease. And so that's important for things like, like a rocket launch. You need to measure how high it's going to go before it starts to come back down, assuming it's not getting out of the atmosphere. So you've got this launch, you need to make sure you've got the space, the room, those sorts of things. And so that's just one very minor example of where knowing where your local maxes and mins could be important. Questions on this example? All right. So here's another one. The figure shows the graph of a function f. At what numbers x, if any, does f have a local maximum? So where are the local maxima located? And so local is not where the function's going to go to infinity. And notice this function is shooting up to the left and the right to infinity. We're looking for any peaks in the function. So we look along and we're chasing, and for this one we're just concentrate on max. So this is only peaks, and our only peak occurs right here. You see it? So the only peak occurs at this point right here, and so that happens at x equals 0. And now to answer Emmy's question from a minute ago, it says list the local maximum values. So where they occur, that's your x's. The actual values are your y's. And so when x equals 0, notice what y is. Y is 3. So the y value tells you the maximum value. The output value, those correspond to our y's. The maximum occurs at x equals 0 with a value of 3. Any questions on A? Good. At what numbers x, if any, does f have a local minimum? Here we're looking for where the valleys occur. So we're tracing our curve along. We see our valley right here. That occurs at x equals negative 2. List the local minimum values. The y value that's associated with negative 2 is a negative 1. So one local min, or relative min, occurs at x equals negative 2 with a value of negative 1. But notice what else happens as you trace the curve along. Do you see this other valley right over here? We know we can have multiple. And so that occurs where? What's the x value? It's at 1. So at x equals 1, and the minimum value associated with x equals 1 is 0. Questions on B? Then C says find the intervals on which f is increasing and also find the intervals on which f is decreasing. So we'll list our intervals of increase and our intervals of decrease. And I abbreviate a whole lot, so if my abbreviations don't make sense to you, please ask. INC, increasing, DEC, decreasing. Okay, we trace the curve. Starting up here at positive infinity, but the function's moving downwards. That is it's decreasing, starting at negative infinity and going to x equals negative 2. Remember here on increase and decreasing, we're just listing the x values over which the increase or decrease occur. Once I hit negative 2, the function is moving up until I get to x is equal to 0. So that's increasing from negative 2 to 0. At 0, the function begins to decrease again, and it decreases until I get to x is equal to 1. So over the x values from 0 to 1, the function is decreasing. Once I get beyond 1, the function increases forever, so all the way out to positive infinity. So this starts at 1 and goes to infinity. Any questions on A, B, or C? Yes. On B, yes. So it's looking for, says first list the values of x for which f has a local minimum. Remember, minimum are your valleys or your dips. So I see those two right here. The x value associated with this point is the -2. The x value associated with this point is a 1. It's kind of hard to read on the slide where I wrote it, but that's an x equals 1. Then we list the minimum values, which are the y's associated with those. So y is -1, and then y is 0. Is that better? Good. All righty. We're building up some ideas about graphing, things that can help us graph, and knowing if a function is even or odd can help us save time for graphing. Formally, a function is considered an even function if, when you plug in a negative x into the function, you get the same thing out that you would have gotten if you just plugged the plain old x in. So f of negative x is equal to f of x. That gives you an even function. Why is that important? Even functions have symmetry about the y-axis. And so if you know a function's even, just graph one side of the y-axis and then use the reflective property of symmetry, and you've got the other half graphed as well. So that's an even function. An odd function is a function for which, when you plug negative x into the function, you get out the original function with all the signs changed. Negative f of x. That's what this negative out here does, is it changes all the signs on the original function. Again, odd functions have a symmetry. The symmetry is with respect to the origin. Origin symmetry is a little bit hard to think about sometimes, but it really can help you. So for example, and pretend I can draw well. So that's, I'm telling you right now, I'm no artist. But let's say that we had a function that had origin symmetry. Origin symmetry means symmetry about this point right here. This is the origin. So origin symmetry means, let's say I had a graph that looked like that on this side. Origin symmetry means if I can pin this graph right at the origin and spin it 180 degrees, the graph would look the same on that side. It would fall right onto itself. So in order to complete this graph, making it have origin symmetry, it would need to look like it did just a moment ago. So notice if I pin this graph right here, and again, stretch your imagination a minute because I'm no artist, but if I were to spin this 180 degrees, it looks the same if it were perfectly drawn. Okay, so that's what origin symmetry is. So notice that in both even and odd, you're going to plug in a negative x. If after you simplify your function from plugging in the negative x, you get out the original function, that's even. If after plugging in negative x, you get out the original function with every single sign changed, that's odd. That's what this negative right here means. You're multiplying by -1. Multiplying by -1 changes signs. Functions don't have to be even or odd. They can be neither. So if you don't get one of those two cases, then the function would be neither. So remember, we have even if f of negative x is equal to f of x, and we have odd if f of negative x is equal to negative f of x. So those are our two checks. So you start with the same thing. Plug in negative x. We're going to see if either one of these two conditions hold after simplification. Starting with A, in A, if I plug negative x into my original function, so remember, when we're plugging in for x and only x. And so for each of these, in place of x, I'm going to plug in negative x. And so f of negative x will be 2 times negative x quantity squared plus 3. Plug negative x into the function where x once was. And now we just simplify. Remember, we're going to take care of exponents first. So negative x quantity squared is a negative x times a negative x, which is positive x squared. So this just becomes 2x squared plus 3. Now we compare that to our original, and what do you see? It's exactly equal to the original, because squaring the negative made it positive. So what type of function is f? This one is even. Questions on A? For B, I'm going to replace x with a negative x. So this becomes a negative x cubed plus 3. Negative x times negative x times negative x. That's what a negative x cubed is. Remember, a negative to an odd power is a negative, so this becomes negative x cubed plus 3. There's nothing more I can do with that. When I compare this function with my original, I see that the sign has changed on x cubed, but it did not change on 3. So this does not equal our original function, and it didn't change the sign on every single term, and so this one is neither. Neither even nor odd. If this had been negative x cubed minus 3 somehow, that would be odd, but it's not. Okay. For C, again, if I plug in negative x where x once was, so h of negative x will be negative x cubed plus 4 times negative x. Over. Negative x cubed, again, that's negative x times negative x times negative x. That's a negative out front with an x times x times x, which is x cubed. And plus 4 times a negative x, that's a negative 4x. What happened? Every sign changed on the original. You can also think about factoring an x out, leaving you with x cubed plus 4x, so that we can formally see that this is negative, and in place of x cubed plus 4x, h of x. So this one is odd. Any questions on A, B, or C so far? I feel a little bit of confusion in the faces I'm looking at. Ask me questions when you have them, please. Okay. So which part is causing you an issue? Are you okay with plugging in? Okay. Sure. So remember, I'm trying, and so for this function, I'm looking at h of negative x to see if it is equal to negative h of x. So one thing you can look at, you don't have to do this part down here if you just say, oh, I look at h and I see every sign changed. That's all you really need to do to say that it's odd. But to show you formally that we are exactly meeting this rule, I went on. But the simple way to do it is just look to see that all the sign changed. So from here, from this step, I could see x cubed was positive, it's now negative. 4x was positive, it's now negative. Every sign changed, that means it's odd. However, to get further down here, if I really wanted to write this in terms of x cubed plus 4x, because notice that's what this statement up here says, it's negative the original. Okay, so I notice that each one of these terms has a negative in it. I can factor it out. If I factor it out, that means that I've already taken care of the negative out front from this term, so that leaves me with the x cubed. Also for this term, I've taken care of the negative out here, so that leaves me with the 4x. So then, that's the negative out front. X cubed plus 4x, that's the original statement of h of x. And so in place of x cubed plus 4x, I can just write h of x. Does that help? Good. Great question. Does that help? Good. All right. We have one more to go, which is D.
So if only one of the signs changes, that would mean it's neither.
That's correct. Yes. So this sign right here didn't change, but that one did. That's
If you have more than two values, and still only one doesn't change, it's still
it's neither. Well, yeah, it's neither in that case, for sure. Yep. So that's a good point that you're making. Every example that I'm doing on this slide only shows two terms, but they can have more terms than that, and it's still the same thing. If you had 6 terms and all 6 terms changed signs, that would be odd. But if 3 changed and 3 didn't, that would be neither. Or if 5 changed and 1 didn't, that would be neither. Okay? Yes. You can just do the first half. Yep. As long as you show me enough work to let me know. What you'll get no credit for it if you show no work, because that's a 50-50 guess, right? You could put odd or even down, and that could just be, I'm not quite sure, but I know the answer's got to be odd or even, and so I'm going to flip a coin, right? And so that shows me you have no understanding of what's going on here. So I want you to show plugging in at least to this step right here on that. Okay? Thank you. Y'all are asking great questions. That makes me super happy. Last one, capital F of negative x. So I'm going to take 1 and I'm going to plug into it negative x, meaning 1 plus the absolute value of negative x. Absolute value is a distance from 0 function. Distances are always positive. So absolute values will always return positive. So if I asked you what the absolute value of negative 10 is, you would tell me it's 10, positive 10. If I were to ask you what is the absolute value of negative 0.62, it's positive 0.62. Whatever's in those vertical bars, meaning an absolute value, you just return the positive. Absolute value of a positive, say positive 5, is just still positive 5. Okay, so positives stay positive, but negatives go positive. So this just becomes 1 plus the absolute value of x, because it's the same. Now, another way you could formally write this is 1 plus the absolute value of negative 1 times the absolute value of x. That's formally what's going on in here. We're taking the absolute value of negative 1 times the absolute value of positive x, because negative x is negative 1 times x. The absolute value of negative 1 is a positive 1, so 1 times the absolute value of x is just the absolute value of x. Okay? What does this look like? 1 plus the absolute value of x looks exactly like the original. And so this is capital F of x, and so this is an even function. Questions on D? Very good. Let me make one other statement over here. Exponents play a huge role in even and odd. If you have a polynomial function are functions that only take coefficients, constant out front, times x to powers. In particular, integer powers. And so, this is a polynomial function, 2x squared plus 3x. Okay. Technically, the x over here is to a 0 power, because x to the 0 is 1. 3 times 1 is 1. When all of your exponents in a polynomial function are even, the function will be even. When all of the exponents in a polynomial are odd, the function will be odd. If you have a mix of even and odd exponents in your polynomial, it will be neither. For this particular situation, 0 is considered to be even. So 2 was even, 0 is even, I have an even function. For the next one, 3 was odd. Remember, this is technically an x to the 0. 3 was odd, 0 is even. You have a mix of odds and evens. This one is neither. For this one, I have an x to the third times an x to the implied first. 3 and 1 are both odd. That is an odd function. That rule does not apply here because this is not a polynomial function because it has the absolute value and it's an absolute value function. And so you can't use that simplification on this last one. Only on polynomial functions, which are functions that look like a, b, and c. Okay? You may have heard that before. So next we're going to talk about a piecewise defined function. This is so blurry. A piecewise defined function is exactly like it sounds. It's a function made up of pieces. So over these x's, you're going to have one piece of a function, and then the next set of x's, you'll have another piece, and so forth. A function that is defined by 2 or more equations over a specified domain is called a piecewise function. So let me show you how we'd write a piecewise defined function. So this is a piecewise defined function. It's a capital C of t. And the way we know that it's piecewise is you're going to see this big curly bracket like this. And it's going to take on 2 different functions. This piece over here identifies the values of the input that go into each piece. So when I'm trying to plug in a t value between 0 and 60, including 0 and including 60 because of the equal signs down here, I'm going to use the value 20. When I try to plug in a t that's greater than 60, that's when I use the second piece of the function. And so these are your directions. These tell you where to go, and they make up the pieces. And so, for example, to find c of 40, this says I'm plugging in a t is equal to 40. When t is 40, the top or the bottom piece is the appropriate piece. Which one? Top. Notice I compare 40 to my instructions over here. 40 is between 0 and 60, telling me that my output is just 20. For 0 to 60, it's a constant function. It's 20 no matter what t value you plug in. If I were to plug in 5, I'm going to get out 20. If I were to plug in 47.35, I'm still going to get out 20 because there's nothing done to t here in this example. Okay. If I try to plug in an 80, notice that 80 falls in the second piece because 80 is greater than 60. So when I plug in 80, I'll get 20 plus 0.40 times 80 minus 60. There is a point. There's a decimal point right there. Any questions on why I picked the second piece for 80? All right. So then we just work through. Remember, please excuse my dear Aunt Sally, I'm going to work inside the parentheses first. So this is 20 plus 0.40 times 80 minus 60, which is 20. Now I multiply. 0.4 times 20, that's just 8. And then I finally add to see that C of 80 will be 28. Any questions on C of 40 or C of 80? Now, there is no reason why you can only just have 2 pieces of a function. You can have more pieces. So if we were to make up a different function, let's just say I've got another function, f of x, which is equal to, let's say it's 3x for negative 5 less than or equal to x is less than 2. Let's say it's x minus 4 for 2 less than or equal to x less than 10. And let's say it's x squared if x is greater than or equal to 10. That's another piecewise defined function, but this one has 3 pieces. But you still treat it just the same. So if I were to plug in x equals 0, piece 1, 2, or 3 for x equals 0. Where would x equals 0 fall? Is that between -5 and 2? Yes. A lot of quiet there, scares me. What is f of 0? You have to compare to see where 0 would fall. Think about a number line. We have some divisions at -5, at 2, and 10. -5, 2, 10. This is piece 1, this is piece 2, this is piece 3. F of 0, 0 is between -5 and 2. That tells me it goes into piece 1. So f of 0 is only in piece 1, so I'll get 3 times 0, which is 0. I guarantee you, every single time I've taught piecewise defined functions in college algebra, when I ask a quiz or an exam over this problem, someone will give me what they get out from plugging in 0 into all 3 pieces. You will get 0 credit from that because that tells me you have no idea what I'm asking, so you're just going to put something on the paper. Okay? So know what these pieces mean. There should be only one output for every input in a function, right? When I plug 0 in here, this is a function. I don't get a choice of y's that come out. There's one x, or an x goes to one and only one y. Okay? And so if you were to give me 3 answers, that would violate the definition of a function. What about f of 2? Piece 1, 2, or 3? Piece 2. So that one's a little bit iffy because it's your change point. It's where we're changing from piece 1 to piece 2, but you're looking for the equal sign down here. Notice piece 2 goes up to 2, piece 1 goes up to 2, but does not include 2. 2 gets included right here, so I'd get a 2 minus 4. That gives me a -2. Okay? So I just wanted to show you a couple of differences there. If I wanted f of 11, 11's over here beyond 10. That means it goes into piece 3. So that's 11 squared, which would give me 121. Okay, questions on that?
So that's what we would plug in, correct?
Say it again?
That's what we would plug for our exams.
Yes. Yep. All right. What about graphing things like this? Well, guess what the graph is going to be? It's going to be pieces put together. It's not just going to be one continuous graph necessarily. You're just going to graph over the pieces. And so what I want you to do when you think about graphing these, you're going to look at where the pieces change. The pieces change at -1. So over here is -1. And you can think, I'm going to have one piece of my function on the left side, and I'm going to have another piece on the right side, defined by my graph here. Okay? Notice that for x is less than or equal to -1, and that's pointing the correct direction, to the left side of -1, less than or equal to -1, my function is 3. That is constant. Remember, constant functions are flat. So up to and including -1, the graph is 3 on the left side of -1. On the right side of -1, my graph will be defined by x minus 2. So if you need to, make a little t-chart. But we're only going to plug in values on the right side of -1. Let's say 0. If I plug in 0, I'll get 0 minus 2, which is a -2. If I plug in a 1, I'll get 1 minus 2, which is a -1. So plotting that. If you recognize this is an mx plus b type function, that should tell you that your graph will be a line, y equals mx plus b. So I'm going to graph that. Now, one little point of concern is that I'm going to have x values, or I could have x values somewhere between a -1 and a 0. Could I plug in a -0.9 into this function? -0.9. -0.9 goes into piece 2. -0.9 is right over here close to a -0.1, but it's on the right side. I could plug in a -0.9, subtract 2, that gives me a -2.9. I could plug in a -0.99, a negative 0.9999999999999, right? Anything that's greater than negative 1 gets into piece 2. And so honestly, you want to graph all the way up to the change point. The piece that includes the change point will get the solid dot. If I were to plug in a negative 1 into this second piece, I know it's not appropriate, but for getting the graph full, I need to do that. So I'll get negative 1 minus 2, which is a negative 3. So here's my negative 3, and the way that I indicate that it's not part of the graph, but it goes all the way up to, but doesn't include it, is with that open circle. So for graphing purposes, you do want to plug in the change point into both pieces. Graph it at the point that it includes the change point with a solid dot. Graph it with an open circle for the piece that does not include the change point, so that you're sure that you've got the graph over all the possible x's. That's kind of a lot to understand because we like to work in integers, but that's not the real world. And so I wanted to just definitely make that point. So what do you see here? You see a piecewise defined functions graph. You see the two pieces graphed. Sometimes they'll join, just depends on how the function works, but many times there'll be a jump. Yes, Jared?
So how do you not get the graph to keep on going down there? Because it's x. So it should, shouldn't it keep going? Like, how do you?
For here?
Yeah.
So notice that for the values of x that are less than or equal to negative 1, so here's negative 1, less than or equal to it, it's just going to be 3. So that's what this is.
Okay.
This part of the function does not come into effect until we get x's on the right side of negative 3. Negative 1. That's what this is telling us here. And so, notice that if I were to keep graphing, let me get over here with the video. If I were to keep graphing this function back over here, it would violate the vertical line test. And so we wouldn't have a function. And so these pieces only start and end where the direction this over here tells you. Does that help, Darren?
Yeah.
Okay.
Thank you.
You're welcome. Anybody else?
The open circle.
Mm-hmm.
Why was that open circle again?
It's open because in this piece, the inequality is strictly greater than. So because it doesn't have the equal sign here, that's where we get the open circle. When you have an inequality with the equal sign, that's where you're going to get the closed circle. Good. Great questions. Hopefully that made that a bit clearer. All right. So the next slide is what we call our difference quotient. The expression f of x plus h minus f of x all over h for h not equal to 0 is called the difference quotient of the function f. For our class, you may be saying, so what? But the so what is because when you move on to calculus, this difference quotient is a basis for all of calculus. And so while we're not going to use it a lot in this class, it does help us as we move on to calculus. And honestly, what this really is just a slope. Let's think about what a slope does. The slope of a line. Anybody remember the formula for a slope of line? It's the m that's in mx plus b, but to get to m, I heard someone starting to say it. Delta y over delta x, change in y over change in x, which you can also write as y2 minus y1 over x2 minus x1. Does that make sense? Y'all see that before? Good. So y2 in function notation, it's just two different function values. So let me show you what we're talking about here. Let's say I have a point x that I'm evaluating my function at, and another point, I'm just going to move along the axis h units. So that's going to be the distance between my two x's. And let's say that I've got a point there and a point there, and let's just make it simple, we'll make it a line. So if I plug x in, remember this is your f-axis. So at this point, if I plug x in, that's f of x. If I plug now, not just x, but x plus h in, that's this point up here, so that's your f of x plus h. Those are your y values. Your y values are your outputs of plugging in the inputs. Your change in y, y2 minus y1. So this is technically the point x plus h, f of x plus h. And this is the point x and f of x. So we look at change in y, that's f of x plus h minus f of x, that's your change in y, over your change in x. Well, your change in x is the larger x, which is x plus h, minus your smaller x, which is just x. Those two x's cancel, and you're just left with h. And so while knowing that, don't worry about it if what I just said kind of went for you. It really is just your slope, and that's where this expression comes from. And so we already know when we study lines that a slope is critically important, but it really is even more important as we move on into calculus. It's about a limiting process that gets us to look at how rapidly functions are changing. But for right now, that's just a little preview of what we're doing here. And so that's your difference quotient. But I'm going to give you step by step how to calculate this. So don't stress. So when we look at our difference quotient is f of x plus h minus f of x all over h. Step number one, we're going to break this up into pieces. Step number one is to calculate f of x plus h. Step number two is the entire numerator. Once you've got f of x plus h, subtract f of x from it. And then step number three is where you take your step number two piece and divide by 3. Okay? Let me write it out a little bit more clearly. So step number one, evaluate your function at x plus h. Plug x plus h in where x used to be. Step number two is to take your result from step number one and subtract off the original. Subtracting off the entire original. So I put some extra parentheses in there on purpose so that you're sure to subtract off every single term and not just the first one. Step number three is where you take your result from step number two, divide by h, and simplify. Those are your steps. You can just go at it all from a big, broad problem and not break it into steps, but I recommend the steps. All right. So here's our function. F of x is equal to x squared minus 1. So remember that when we're plugging things in, sometimes we might want to put an extra set of parentheses around the x. This in particular can help you on this x plus h part, the very first step. Step number one, evaluate your function not at a plain old x, but at x plus h. Plug x plus h into the function. So this is equal to the quantity x plus h squared minus 1. So what used to be inside f's parentheses was x. Now I'm putting x plus h, so x plus h goes in to the parentheses wherever we once had an x. Okay. Now remember, x plus h quantity squared requires full, because it's x plus h times x plus h. First, x times x is x squared. Outer is x times h, and inner is also x times h, so we have two of them. 2xh. Last is h times h, so that's h squared. And I bring down this negative 1. Okay. That is step number 1, f of x plus h. Any questions on how we got there?
Where did the 2 come from in that?
Sure. From the O and the I of full.
Oh,
Okay? First, x times x is x squared. Outer is x times h. Inner is also x times h. That's 2 of them. And then finally, h squared.
oh, I get it.
You're welcome.
Are we going back to like the last problem? Because like the x minus h, y, like where are we? Because I don't really understand. Like why are we doing x minus h or x plus h?
So, x plus h, that's a great question. So, used to, when you talked about slope, you would just say, I've got 2 points. This one is x1, y1. This one is x2, y2, right? And so you've got a line that joins them. When we calculate slope, it's change in y, y2 minus y1, over change in x, which is x2 minus x1. Is that okay so far? Remember that? Now, generically, instead of talking about knowing the actual points, we can just say, let's just say that my x is changing by some distance h. So I'm just going to say, how much am I changing x? So if I started at an x and I increase it by h, then my new x value is an x plus h. And the reason for this notation really has to do with some pre-cal and some calculus stuff, because we're going to let h basically go down to 0. And so it's about saying, what if I just change x very minimally, almost by nothing? And so that's to come. That's why this notation is like it is. But the h is really just the distance between the two x's. So that's why there's just an h down there.
So could h be anything? H is just a variable, right?
H is just another variable, exactly.
That's what.
Okay, good point. Good question. Okay, so step number 1's done. Any questions on it? Step number 2 said to take what you get in step number 1 and subtract the original function from it. So what I got in step number 1 was x squared plus 2xh plus h squared minus 1. So I'm just copying that right down. That was step number 1's answer. Now I'm going to subtract from it the original function, which is x squared minus 1. You can see why the parentheses are important here, because I'm not just subtracting the x squared, I'm also subtracting the minus 1. The entire original function gets subtracted. I'm going to go ahead and remove these parentheses on the original function by distributing the negative 1 through to the x squared and to the negative x. So this is negative x squared, and then negative and negative 1 gives me a positive 1. So that really shows you the importance of that set of parentheses there, because oftentimes if you didn't have the parentheses there, you'd forget to change the sign on the negative 1. Now we collect like terms. I have an x squared, and then I subtract the x squared. Those actually add to 0, so they cancel. They're gone. I have a negative 1, and I add a positive 1. Those add to 0, so those are gone as well. So that the result of step number 2 is 2xh plus h squared. It's long, but it shouldn't be difficult. Okay, just follow the directions. It's telling you exactly what to do. Finally, step number 3 says take what you got in step number 2 and divide through by h. My result from step number 2 was 2xh plus h squared. I'm going to put that all over h. And notice what else I said about step number 3? We're going to simplify. I bet a great number of you want to cancel this h with that h. That's not right. You can only cancel when you can pull that same thing out of everything up top and everything on bottom. which is good because I have an h in that term and I have two h's in the second term. They share one h. I can pull the one h that they share out. If I factor an h out of the first term, I'm left with a 2x. Factoring an h out of the second term, it had 2 in it, so I still have 1 left. And now over h. What canceling really is creating a 1 out in front. You did not have the 1 out in front of everything if you only canceled with the first h. So now we've got our simplified version. This is just 2x plus h. And we're done. Questions on A? Are the steps helpful? Okay. I see a little bit of uncertainty here and some faces, but that's okay. We'll do some more. Actually, before we move to B, I want you to try one. Let me give y'all one. I want you to find the difference quotient. It's going to be similar, so let's say A number 2. I want you to find the difference quotient for f of x is equal to, let's say, 3x minus x squared. So I want you to try that one. If you need help getting started, let me know. You can use your notes from the prior one because we're still learning. Just basically mirror the steps that we did in A. You can help your neighbor out too, so I appreciate that. You can work together if you want. So let's go ahead and get the Christine around x and now that's where your explanation. So that's what this is telling you. What used to be in appendices was an x, now it's an x plus an x. Yeah. That's a great start. Perfect. Yes, you got it. You did it and then the negative 1, I think you just copied that one. It wasn't. Negative 1. Does that make sense? That's correct. Yes. Great. Yes. For this one, it will be. Yes. So when you get to this x squared, it's going to look like what we had just a minute ago. You're welcome. Honestly, for these types of problems, these polynomial type problems, the first step is the hardest. So yes, so on this one, we've got our original function. Let's go ahead and use the parentheses like I have done, like this step here where I put the particular x and only x plus 2. So let's rewrite this and write x for this one. And then 3 open parentheses. So notice that what we call as parentheses here is exactly what was going to touch it. Okay, so now that's what what you're doing. Now it says where x used to be. I'm going to take this that so wrong.
Yeah, you subtracted negative.
And then the x plus x squared was
Plus 2
is the way I got it.
plus your second.
Yeah.
But then I'm stuck on this. Yeah.
Plus 2x
Stuck on the.
plus
Like when you originally said.
So on this one, you're going to need to
Oh, that's right, okay.
and I was get that minus sign is everything. Yes, yes. So you were close, you were just missing the middle.
Okay, so on the second step, so I put that as
The second step is where you subtract the original.
So remove the 3 to x.
For me, it's just like
All right, so I wanted you to kind of get started, and even sort of part of me wanted you to struggle a little bit, because that's okay. That's where we learn the most. And it was okay if you didn't struggle at all, too. But because if we can catch mistakes right here, that's the place to do it, right? So let's go ahead and see what this looks like. If it helps you, and for many of you that I was seeing, the parentheses trick can be very helpful. And so we're going to be plugging in x plus h into our function. And so I'll rewrite the function as 3 with the parentheses x minus parentheses x squared. So that when we plug in, this becomes 3 times the quantity x plus h minus x plus h squared. Okay? So that really is 3f of x plus h, but we want to go ahead and expand it out because we want to simplify eventually. So the 3 distributes through to the x and the h to give me 3x plus 3h. Okay. And then minus what I get when I use full here. X plus h squared. You're going to probably have an x plus h squared in your problem on the quiz on Wednesday. That's your full. That's x squared plus 2xh plus h squared every single time. So from full, we know that we get x squared plus 2xh plus h squared. The reason I put it in parentheses is that the negative, because of order of operation says square first and then multiply by the negative. The negative applies to everything from the full. So this is 3x plus 3h minus x squared minus 2xh minus h squared. That's step number 1. There are no like terms left in there, so we're done with that part. So that was step number 1. Step number 2 is where we take what we got from step number 1 and subtract the original function from it. 3x plus 3h minus x squared minus 2xh minus h squared. All of that's just step number 1. We subtract our original function, which is 3x minus x squared. Notice that we're subtracting each of these. So at this point, if you want to simplify here, you can. Saves you just one step of writing. I have a 3x. I'm subtracting from it a 3x. So that 3x and that 3x add to 0 because of the negative out front. I have a negative x squared here, and I'm subtracting a negative x squared. So negative x squared minus itself, those will add to 0, so those are also gone. So I get 3h minus 2xh minus h squared. That's step number 2. Finally, step number 3 says take what I got in step number 2 and put it over h. That's 3h minus 2xh minus h squared all over h. I notice every single thing up top has an h in it, so I can factor an h out. Factoring an h out of the 3h leaves me with a 3. Out of the negative 2xh leaves me with the negative 2x. I've factored 1h out here, so I'm left with 1h. And then over h, so that I can finally see that I made my 1 out front. So that's the cancellation. And so finally, the difference quotient is 3 minus 2x minus h, and that's the final answer. For polynomial type functions, which is what we've seen in both A and A number 2, this is the process. One of the things you might have noticed is that in step number 2, we wind up canceling everything that's in this parentheses over here. That will happen every single time for a polynomial function. Okay. So that's a couple of examples on polynomials. Things do change, and I do have these slides up here. If I moved one too quickly, you're welcome to always come up here and grab and dig through them, or you can go back on the video and pause it once I publish them on Canvas. Things do change a little bit when we get into a rational type function. So here, our function f of x is 1 over x. We want to find the difference quotient, f of x plus h minus f of x all over h. Step number 1 is to take where x once was and plug in x plus h. So if you want to use the parentheses, this function looks like 1 over x, where x is inside the parentheses on the bottom. Evaluating f at x plus h instead of just a plain old x looks like this. And that's all you can do with that one. So step number 1 in this rational function is easier. So that's step number 1. Step number 2 is where you take f of x plus h and subtract from it, or what you got in step number 1, and subtract from it f of x. Step number 1 gave me 1 over x plus h, and I'm going to subtract the original, which is just 1 over x. This one seems easier so far. Step number 3 is where things get interesting on rational functions. Step number 3 says take your result from step number 2, put it over h, and simplify. And it's the and simplify part that will give us some interesting pieces. So we've got 1 over x plus h minus 1 over x all over h. Okay. Any questions about how we've gotten here so far? Literally, we're just following the direction. The simplification part on here. The reason we want to simplify is I have fractions within a fraction. This is called a compound or a complex fraction. We want to get rid of those. Remember, to simplify, we want to make things look different but not change their value. And one way we can do that is by multiplying by 1. If you multiply something by 1, it doesn't change its value. But the challenge is, what does 1 look like? And the trick for these, the 1 is going to look like finding your common denominator in the complex fraction, which is just an x plus h times x. But I can't just multiply the top by it. I have to multiply the bottom by that same thing. So where did I get these values? I got them from the denominators that are actually in the numerator, the complex or compound fraction pieces. Okay? But I can't just multiply the top by x plus h times x. That would change it. But anything over itself is 1. So this is just a complicated way to write a 1. This equals 1 because I have something over itself. So I'm not going to change the value of my function if I multiply it through by that. I'm going to take what's up in the numerator and distribute it to each of these fractions. To help us see things easier, this is just going to be the way to do these. Do not distribute through in the bottom. Just leave it in factored form. Okay, so the top. I have x plus h times x multiplying by 1 over x plus h. So that's x plus h times x over x plus h minus x plus h times x over x all over h times x plus h times x. So everything got multiplied through by x plus h times x. Every single piece. But now everything up top is multiplied by x plus h and on the bottom, so those cancel. And it's the x over here that cancels. So what I'm left with up top for the first term is an x minus x plus h for the second term all over h times x plus h times x. So the top becomes x minus h when I distribute the negative sign through, all over h times x plus h times x. X minus x, those add to 0. I'm left with a negative h over h times x plus h times x. One more simplification. Everything up top has an h in it, and everything on the bottom is multiplied by h. So that h and that h do cancel, and I'm left with negative 1 over x plus h times x. And that's the final answer on that one. Step 1 and 2 were relatively easy. Step number 3 is a bit of a booger. But that's the way these will work every single time. And it's what I wrote in red, and I intentionally wrote it in red because that's the highlight of this problem, is what 1 looks like. We do have one more example. When I get to my office this afternoon, I'm going to go ahead and record it, and you can go on and watch that for class next time. Part of your homework. One more example.